Alright, field transistors, field effect transistor, Eugenian, Aiden Mikov, collector William Mary, week 8. Junction effect, field effective transistors, negative junction field effect transistor goes drain, gate, source. Positive joint field of transistor, drain, gate, source. Metal oxide semi-containers of MOSFET. Gate is truly isolated. There's fourth terminal usually connected to source. Negative MOSFET, positive MOSFET. Field effective transistor pros, very high input impedance. Joint field effective transistors impedance of 10 to the 12th ohms. MOSFET impedance 10 to 14 ohms. Thus, very small current to a base of picoamp range can operate bidirectionally. As a result, very little power consumption of biasing network. Field effective transistor cons have large parameters and spread. Let's focus on negative junction field effect transistors. Generally negative channel, usually faster due to the higher mobility electrons versus holes. Currents goes through the drain source, thus the names. Drain source are nearly identical, thus the gate is centered at some diagrams. Gate, drain, and source can be used backwards and almost same performance. Arrows indicate the direction of positive negative junction. This normal operation low current owing to the gate. The voltage gain is greater than the voltage source. Alright, VP to pinch off voltage, intrinsic parameter voltage, pinch off is less than 0 with the negative junction field effect. Negative junction field effect transistors is also called the voltage threshold of the metal oxide field effect transistors. Voltage gain source is less than the voltage pinch off voltage, and amp drain is equal to 0. Voltage gain source is greater than 0.6. Device fails. Remember about the gate diode. Voltage pinch off is less than voltage gain source is less than 0.6 volt. Normal operation. Amp drain is times voltage gain source and voltage drain source. Linear region. We see that voltage drain source is less than voltage gain source minus voltage pinch off. Saturation region, voltage drain source is greater than voltage gain source and minus voltage pinch off. K is constant. Shows in linear region, saturation region, drain source voltage, and current in milliamperes. Another picture. This was real amp drain versus voltage drain source, linear region. Real ampere drain, voltage drain source, linear region. Real ampere drain, voltage drain source, saturation region. Saturation region depends on voltage gain source and voltage pinch off. Reading specifications. Then it shows the negative joint effect field transistor voltage current divider. So we have the base, the voltage current going to the base, the drain voltage input going through resistor, drain, the voltage output, ampere going to the drain, emitter, so the ground. Negative joint compensated voltage control divider, voltage control resistor 1, resistor 2, base, voltage out, voltage in, drain. Negative joint field effect transistor constant current source. Shows voltage DD, resistor inductance, ampere drain, base, resistor source. Field effective transistor voltage GD and voltage in, voltage out, resistor source. Voltage out equals voltage in, voltage out equals voltage in. And that's in your field improved. Alright, Chapter 8, Field Effect Transistor. Transistor. The different basic elements of the electronic elements have three terminals with a consequently we need more of the parameters because of the behavior of the simple current voltage characteristic. We found that thinking of the transistor as the current amplifier, particularly useful mode with the model, however, it does have its limitations, we can extend it to. Next step is with the transducent come out over the Elbers-Moll model. Then this improved the model. The collector current depends upon the base emitter voltage. With the process of the base emitter voltage produced the ampere current collector. In this model, voltage base emitter, it also produces an ampere base. So this model includes the earlier current with the amplifier model with the addition of the new features. 1. Field effect of transistor. In addition to the field effect transistor, with the weak with the new element called the field effect transistor FET, but also the three-terminal element. The three-terminal element is some of the transistor base, the emitter of the bit collector, and then they call the gate, source, and drain. The initial field effect transistor will use have an identical package of the transistor even earlier than the semester. With the schematic symbol with the field effective transistor will be also shown in Figure 8.1 on the right. So now we're having the arrows going to and from the right. The left would be a negative channel, the right a positive channel. Field effective transistor produces a single piece of the conducting silicon that connects the source of the drain with this called the channel with the gate with the create with a different feathered connection with the gate with the voltage applied with the control with the conductivity of the channel. The gate channel junction looks over the diode with the never conduct ends of the gate draw with no current with a major difference with the normal transistor field effective transistor. The consequently field effective transistor with extremely large gate input impedance of the less greater than 10 to the 12th ohms. There will be force with the chart with the modeling device for the transducent model where the drain collector current depends on the gate voltage, not the current. This is the major difference between the bipolar diodes used in the previous field effective transistors. Field effective transistors are extremely important input stage of the amplifier since they such with a large input impedance to also attain the ideal measuring of the voltage without drawing any current from the source. This is great if you want to measure small voltage charges, plus on capacitors if you want to do a particular detector. Field effective transistors come in 5 general types. We will restrict ourselves with the joint junction field effective transistors. In our example, use the only negative junction field effective transistors. They have a negative channel with a negative channel doping, and similar with the negative transistor with the positive channel joint field effective transistor require an opposite of the voltage on the gate. They usually get with a poor performance due to the lower mobility, shorter lifetime holes of the holes and compared to electrons. As mentioned above, source drain current, the only current with a flow through with the field effective transistor with a source for the drain current and the label the ampere drain. The voltage applied with the gate terminal enables the current with the current electrical field inside of the train with no fundamental difference between the source of the drain terminal and the joint field effective transistor. The gate drain capacities, however, are usually lower than gate source capacities, so that they are used in space specified. This is because of from the normal transistor, some of the current can flow over either the drain source from the source to the drain. Note that the maximum minimum value of the gate voltage in order to keep the device operating the joint field effective transistor, the diode joint separating the gate with the channel, but the gate must help with the voltage less than 0.6 volts above the channel with a usually source terminal. If the gate voltage becomes greater than the junction, becoming an conducting gating current would no longer be zero, but usually will not be let voltage between the gate and the source of voltage gate source and source greater than zero. But if the gate is biased for the two negative, no current flows for the channel is said to be pinched off. The minimum gate voltage of the voltage pinched off is the characteristic that varies with one model with the joint field effective transistor. Usually ranges from -3 to -10 volts, and even with the same with the type of the field effective transistor parameters vary significantly one device to the next. Let's summarize the property for voltage gain sources less than voltage pinch off. Amperes drain is equal to 0. Voltage gain source is greater than 0.6 and device fails. When voltage gate source is between those of the ampere drain depends on the voltage gate source and the voltage drain source. Complete description of the device would require the two-dimensional plot showing that the ampere drain varies both the voltage gain source and voltage drain source. B. Both regions of the operation. For a fixed voltage gain source of the basic behavior of the drain current with the function of the channel with the voltage shown in the figure 8.2 with above with the behavior of the simple model within two regions with a small value with the voltage drain source with the almost proportional voltage drain source just like the resistor. This is called the linear region. The reasonable larger value of the voltage drain source for the amperage drain has been little dependent of the voltage drain source. This is called the saturation region. The actual relationship with the condition approximated as for voltage drain source is less than voltage gain source minus voltage pinch off. The amperage drain is equal to K times 2 times voltage gain source minus the voltage pinch off times voltage drain source minus voltage squared drain source. For voltage drain source greater than voltage gain source minus voltage pinch force, an ampere drain is equal to K times voltage gain source minus voltage pinch off squared. And those are your linear and saturated region. For small enough voltages, quadratic terms in the small, in this case the current of the linear region proportional voltage drain source, just like the resistor, true enough with the negative voltage drain source, so the amperage drain source with the proportional both of the voltage gain source with the voltage gain source gives us makes of the voltage controlled resistors. More, since amperage drain is proportional to both voltage drain source and voltage gain source, we can generate the current corresponding to produce the two signals. In a saturated region, the amperage drain nearly independent of the voltage drain source. We can use this to make the excellent source of the followers that are similar to our transistor-based emitter follower to much larger input impedance. Note that the region there is a small slope. Slope increase the large gate voltage. We'll discuss the saturated region later in this chapter. See the IC voltage controlled resistor. For equation 8.3, we can use the drain current with the proportional voltage drain source, whether when the voltage drain source is small with the proportional constant of the proportional voltage gain source. This is perfect for the making of the voltage controlled resistor. A typical data sheet list of the voltage drain is on the resistance measure for the gate is shorted on the open source. From equation 8.3, we see that voltage resistor drain is on approximately 1.5 kilo voltage pinch off. You must put the resistor in series of fixed resistor. Then you have the voltage controlled actuator. If this followed with a procedure amplifier, the combination would be an amplifier voltage controlled gain. Figure 8.3 shows uncompensated voltage divider. So we have the negative 15 volts at 10 kilo ohms, rail resistor gain, resistor drain, a voltage input, voltage output, base emitter, and it's going both directions. And then, so an 8.4 shows the compensated voltage divider, where there's a resistance capacity. By making the figure the resistor drain with the field effective transistor and resistor A3 with the voltage divider actuated with the input voltage side with the equivalent resistor and field effective transistor determined by the voltage gain source, which is set by the potentiometer. With the making of the right choice for the gate voltage, improve the trick with the eliminating quadratic term in equation A3 for the improve the linearity of the actuator from the equation A3, as we see, is 1 over the resistance of the drain source and equal to amperes drain over the voltage drain source. If we see that the voltage drain source is exactly voltage drain source divided by 2, then we find resistor drain source is equal to negative 1 over 2 times K with a voltage pinch off. Figure 4 shows the version actuator employed with the improve the linearity. 2 resistors connect with the gate, force half of the drain voltage onto the gate. They should be large enough that the potentiometer with the capacitor just blocks the DC so that only a single part of the input voltage fed to the gate with the application amplitude with the modulator. If you find a second lower frequency signal with the gate in addition with the DC voltage potentiometer, then you can modulate the actuation over the voltage divider. Of course, you should feed those capacitors so that they have not distributed coincidentally with the condition 2 of the saturated region. As we saw with the equation 4, with a larger value of the voltage drain source, the drain currently only depends on the voltage gain source. Ampere drain equals K times voltage gain source over the minus voltage pinch off squared. Saturation useful, for example, the making current sources involved with the distributed early, still some of the dependence of the amp drain on voltage drain source. Even in the saturated region, you can, however, reduce the effect with a few extra tricks. A, transducency of the field effective transducer is denoted as GM, defined as GM is equal to the 8989 and 810. Alright, transducing usefully understanding the behavior of the field effective transistor and interpret the slope of the ampere drainage for the verse of the voltage gain source of the saturated region depending on the choice of the ampere drainage. Converted transducency of the voltage gain source of the transducency of the ampere drain, usually shown with a data sheet that have complicated shapes known that have the value with set conditions. You can use it above the relation scale with the other similar values. Transducing units of the negative 1 is known with the MHO, they're pronounced MO. You often see units of the UMO, or micro micromho. For 10 to the negative 6 mho and millimho for 10 to the third and millimho in FE field effective transition specification. You might use the inverted capital omega or S to represent that unit. The remainder of the section will cover some application field effective transition employing saturated region. B. Joint effective transistor current source. You can easily make a field effective transistor current source by connecting the gate to the source with applying high enough voltage to the drain with the joint effective transistor operated saturated region. Figure 1 generates the current through the load of this is specifically current with the IDSS, whereas the subscript denotes the drain current when the gate is shorted or shorted. So we have drain shorted. According to transducer model given in equation 3 and 4, the saturation of the amp drain source shorted when the gain voltage gate source is 0 is given an amp drain source short is equal to kill voltage pinched off. The two terminal joint effective transistors are exactly circuited to packages to look like diodes sold under the current regulator diodes. Since we know there are large variation voltage pinch off, there may not seem like the best specified device. In fact, when the marketing device the manufacturer actually measures the response of the other devices on the prototype, there may be roughly specified current within a factor of 2 or 7 milliamps. So this is called the pre-selection common of some of the categories commercial electronic production. Also, the device is very large variation of photodetectors. Since they're expensive, the companies invest huge amounts into the develop the more expensive components in CPU chips, the disk drive heads, and improve the quality control of them during fabrication. Alright, you can make the circuit absolute with a programmable constant current source by adding the resistor between the gate and the source to provide an offset with a figure 5. Since there's voltage drop across the resistor, the current is ampere drain times K with the time of the voltage gain source time of the voltage pinch, minus the voltage pinch times 2. Which is equal to K times negative R at the resistor at the source times ampere at the drain times minus voltage pinch off squared, are also equal to amp drain source short equal to resistor source amp drain short source times resistor source times amp drain over voltage pinch off plus 1. 8.5. The programmable constant current source driving a load. We have a resistant load resistor source, and the resistor source goes back to the base emitter, and the rest is grounded. This can be solved with the input drain, but rather ugly in practice. One normally starts with the plot with the ampere drain versus voltage gate source with the device data sheet with the roughly idea of source resistor. Some of the saturation properties are not well determined in the fabrication process up to the factor of 10. Use parameters if you wish to sync the specific current. CJ, the joint field effective transistor follower. The draining of the current joint field effective transistor with the operating saturated region depends on only on the voltage gain source. Because of this, you can add a source resistor field effective transistor provided with negative feedback, but this is called source follower. Follow quiescent state where the nominal value of the amp drain and the voltage gain source. Increase the gate voltage, increase the current with the source resistor. This will call the increased voltage drop the raise of the source of the voltage conventional with a lowercase letter that represent the small variation quiescent points. In our transition models, they are variation of the governed by amp drain equals to GM plus times voltage gain minus voltage S. Source of voltage dropped across the source of the resistor. Voltage source equals amps drain times resistor short. These two equations find it out. Figure 8.6 shows a simple source follower. Voltage drain VDD, voltage input, voltage output, resistor source. Our field effective transistor. From equation 9, we can see that the source of the follower acts like the voltage divider with the field effective transistor behaving like a resistor of the 1 GM. This of the voltage divider to determine the output impedance of the field effective transistor. Small resistor of the divider of the output will not be very close with the gate. With the output impedance of the source follower, there's 1 GM. The output impedance for the typical a few hundred amps and the current few milliamps. So our simplifier, however, that does not behave well with the voltage gains will vary with the nonlinear transducing distort the input. If the quiescent output voltage is specified with the pinch voltage of the device, hence when it is unpredictable, they require voltage gains for us to produce the quiescent current varies a lot from one device to the next. The output impedance is relatively heavily hot. On the good side of the input impedance is immense. A matched pair follower, a very common solution to replace the ground end of the source resistor for the current source is called the active load. Putting a constant current sink, we always have the same amp drain fixed voltage for the voltage gain source. The first problem is solved with it does not have the fix other problems. If you don't even better with the job knowing within the manufacturer verification field effective transistor, significantly smaller field effective transistor made from small pieces of silicon wafer and die. You think of it maybe the identical twins instead of just siblings. This is called the match pair or example of the match pair joint effective transistors. Using second joint effective transistors, active loads get rid of the most problems. Field effective transistor figure 7. Second joint field effective transistor keep the constant current with a fixed voltage gate source. Eliminate the non-linear and matched resistors. Add also the ampere drain predictable. Furthermore, you match the field effective transistor with a pair of the symmetric power supplies. Largely eliminates the DC offset with the output. To fix the power output impedance, one would need to add an operational amplifier follow the amplifier to the output. Match pairs give the input stage most of the charges unmeasured with the application oscilloscope's input sensitive. The electrometers measures the small charges like one seen in the particle detectors, current pre-amplifiers, and photodetectors. Figure 8.7 shows a match pair figure. So we have a 10 volt voltage in, voltage to match pair, resistor S, source, design exercises, labs, and we don't do those because this is just a reading of some college work.